So actually what I'll talk about is not just about the non-nef locus, but rather try to put together and discuss in general asymptotic base loci. And again, what I want to insist is about some techniques that work in positive characteristic when you look at these base loci. So let me actually start by explaining a little bit what are these base loci that I want to look at. So all the time, I'll just deal with, let's say, X will be a projective scheme over some algebraically closed field, which in a little bit will have characteristic 0, characteristic P. And if you prefer, you can take X to be a smooth variety. So for some of the results that I'll talk about, it's actually quite important to do things more generally. And let's say that L is a line bundle on X. And again, I'll switch back and forth between line bundles at Cartier divisors. So let's say that I have, if I have a section of L, right, so then there is the 0 locus of this section, which is a closed subset of X. I guess it's a closed subscheme of X, right? And the base locus of L is, again, it is a closed subscheme, which is the intersection of all these 0 loci of S. All right, so S is a section of L. Okay, and of course, this is very important because you want to know when L actually defines a morphism to a projective space, and in general, you want to know where the rational map defined by L is defined. All right, but this is, of course, in general. I mean, if you want to look at an arbitrary line bundle, this problem is quite tricky. So the first approximation is not to look just at the base locus of L, but rather as something of a more asymptotic nature, which is a so-called stable base locus. So let me remark first, one thing is that if I take, so for example, if I compare the base locus of a multiple, let's say L to the M, right, with the base locus of a multiple L to the MR, right, and if I take the reduced structure on these sets, right, so certainly if I have a section of L to the M, if I take its rth power, I get a section of this line bundle. So if I just look at the reduced structure, I mean, the 0 locus is the same. So in other words, I get this sort of inclusion. Right? So what this says is that by the Noetherian property, if I keep letting M be more and more divisible, these things stabilize. So what I get the stable base locus, or the asymptotic base locus, B of L, which by definition is the intersection of all these base loci, the reduced base loci of L to the M, with the reduced structure. And again, this remark over here says that actually this stabilize if I take M divisible enough. So this is really the base locus of L to the M with the reduced structure for M divisible enough. Okay? So again, so this is again a very important object, right? So this is empty if and only if some multiple of L gives you a morphism to the projective space. In other words, if and only if L is semi-ample. So of course, you'd like to be able to decide in various situations when such a line bundle is semi-ample. But the trouble is that this is not a numerical notion, right? So you can have two numerically equivalent line bundles such that the corresponding loci are different. So for example, if you take L to be something that's numerically trivial, then this base locus is either empty if L is non-torsion, or it's empty if L is torsion, right? If some multiple of L is trivial, then of course this locus is empty, and otherwise it's just the whole thing. So again, from this point of view, it's not so well behaved. On the other hand, of course, by definition, what's clear is that B of L is equal to B of every multiple I take, right, for every R, because this really depends just on some very large multiple. So in particular, I can extend the definition to work not just with line bundles, but rather with line bundles with Q coefficients, right? So can extend the definition to pick of X twisted by Q. Okay, and typically when I work with line bundles with Q coefficients, I'll use the language of Q divisors. Okay, so. All right. So what are actually the loci that I want to talk about? So the basic idea is that you want to twist a little bit the line bundle by an ample, by a small ample thing. And you can do it in two ways. You can do it either by adding a small line bundle or by subtracting a small ample. So then you end up with the following loci. So the first one is called the augmented base locus. So this was introduced by Nakamae in a paper that somehow initiated this look at this augmented base loci, Nakamae. So this is the following. So maybe, actually, before giving the definition, let me make one trivial remark, which says that if I have B of L1, right, and B of L2, so if L1 is more positive than L2, in the sense that L1 minus L2 is ample, right? Since, of course, an ample guy, by taking a multiple, I can just move it, so it has no base points. So this is actually smaller. Okay, so this is trivial. All right, so now what I want to look at is this augmented base locus is B. I'll write it B plus of L. So this will be, by definition, the intersection over all A ample of this stable base locus of L minus A. Okay, so because of this, but ample, not just line bundle, but in principle Q divisor or Q line bundle. So, all right. So what do you see, right? So I subtract something ample, so this will be less positive. So the locus will be larger than B of L. On the other hand, you should think of A as being very small, right? Because when A gets smaller, so this, by this inclusion, what this means is that the locus itself gets smaller, right? So if A is ample but somehow very small, this locus gets smaller and smaller. So in particular, again, using Noetherianity, right? So this set actually stabilizes. So for example, one way to describe it is, so this is equal to B of L minus epsilon H, where H is, for example, a fixed ample, and epsilon is some small rational number. Okay, so again, the moral is that you want to subtract a very small ample. All right. And by symmetry, right, you can do the other thing. So I'll denote B minus. So this is the so-called non-nef locus. So this is, again, so now I'm going to add something, and I'm going to take the union. Again, I look at all ample Q divisors, and I'm taking B of L plus A. And again, right, so when A gets smaller and smaller, this locus gets larger and larger. So somehow you have a union. All right, so what do you see if you stare at these two definitions? First of all, let's see, for example, when is B plus of L empty? Right, so it's empty if and only if, right, for some A, for ample, L minus A, or some multiple, has no base locus. Right, but what this means is that it's ample plus something that is base point free, so this is ample. Right, and conversely, if L is ample, I just subtract a small multiple of itself, and I get empty. Right, so this is if and only if L is ample. So what about the second locus, B minus of L? So this is empty if and only if. So let's look, right? So this is empty if and only if when I add a small ample, I get something that's base point free. Right? But what this means is that L itself is actually a limit of base point free things. So in other words, it's nef. And conversely, if I have nef plus an ample, is ample. So by the way, nef means that it intersects non-negatively every curve, right? Or equivalently, it's a limit of ample divisor classes. Okay, so this is equivalent with L being nef. Okay, so the way you should think about it is that this locus somehow is precisely the locus on which L is non-nef, and the larger locus is the one on which L is non-ample. Right? So by the way, so this is smaller, right, than the stable base locus. So this is contained always in B. Okay, so you get these approximations. And the way they are, I mean, the first reason why they are good is that they only depend on the numerical class. So both B minus of L and B plus of L only depend on the numerical class. Right? And the reason is trivial because, I mean, I define them in such a way that basically I add ample divisors, right? But ample is a numerical notion. So if I replace L by some L prime, such that L and L prime are equivalent, of course, I mean, I can replace one A prime, A by some numerically equivalent, which is still ample, and I still get the same locus. So somehow by default, I mean, I get built in this dependence only on the numerical class of L. Right? So then it will make sense to ask, how do you describe numerically, in terms of some function defined on the cone of, on the set of numerically equivalent divisor classes, these two loci? Okay, but one last general remark is that, you see, again, B plus, so this augmented, this large base locus, is an intersection of closed subsets, right? So B plus is actually a Zariski closed subset, B plus of L. So at least a priori, this one is not. So this is a union of such closed subsets. And in fact, you can take, for example, you can take A to be the set of all multiples or rational multiples of a fixed ample divisor. So it's easy to see that actually B minus of L is a countable union of closed subsets. And the basic question, somehow it's a bit annoying that one doesn't know this, is, so is B minus of L also closed? Okay, so I think that the expectation is that in general, this will not be true. So there should be line bundles for which you really have a countable union of closed subsets. But on the other hand, one doesn't really know too many interesting examples. So it would be nice to actually have a concrete example where this doesn't hold. So another reason for this question is the following remark. So for those who know about Zariski decompositions, right, so if L has a Zariski decomposition, let me say just in words what this means, right? So this means that you can write it as a positive part plus a negative part, such that all sections of multiples of L come from sections of multiple of the positive part. So for example, this always happens if X is a surface. Okay, so in this case, actually B minus this non-nef locus, B minus of L, is the support of the negative part. So sometimes you do this Zariski decomposition on some model upstairs, but and then it's the image. So support of the negative part in the Zariski decomposition. Okay? So if you don't know what the Zariski decomposition is or haven't seen it, don't worry about it. So, but somehow the idea is that in general, there is no such Zariski decomposition. But this B minus of L should give you some sort of geometric object that should play the role of the support of the negative part in the Zariski decomposition. So you see in particular that if, for example, you find an example where this locus is non-closed, right, so this gives you a very strong, very strong statement of non-existence of Zariski decomposition in that case. Okay? So any questions so far? So yeah.
So what about B class? Does this have some interpretation? Something analogous to the Zariski decomposition?
No, not really. The main purpose of the talk is to explain some characterization of this loci. But no, it's not related to a Zariski decomposition. right? Because the Zariski decomposition is something that basically you do when you want to reduce some divisor to a nef divisor, right? So somehow you would want, I mean, B plus is more related somehow to some sort of ample part, whatever that would mean. Okay? So in general, you should think of, so B minus is some sort of correction for B itself. So for example, if the section ring of L is finitely generated, then actually B minus is equal to B. Right? Again, this is non-trivial from what I said. But B plus, I mean, typically can be quite different. So anyway, so this is about the definition of these two loci. So now let me state the main results, and then I'll switch to characteristic P and to say a few words about somehow what's special in characteristic P. So the first theorem. All right. So now from now on, I guess maybe I should say from the beginning. So I have so the characteristic of K will be positive. So the first theorem, which is joint with Paolo Cascini and James McKernan, says the following, that if L is big, well, I guess I don't need to put it. Sorry. So let me say. So if L is an arbitrary line bundle on X, which is nef, then you can describe this B plus in the following way. So B plus of L is the union of all, let's say, V, where V is a irreducible closed subset, such that L restricted to V is not big. Okay? So one remark is that since L is assumed to be nef, right, so the restriction of L to such V is nef, and therefore this condition of bigness, right, so this condition here is equivalent, well, first of all, that V is positive dimensional, so dimension of V, let's say R, is positive, and the self-intersection of R restricted to V should be positive. Right? So since L is nef, this self-intersection is always non-negative, but this bigness condition says that this self-intersection is positive. Oh, sorry, not big. Oh, I messed up. Thanks. That's right. Okay, so in this sense, this is a numerical description of this locus. Right, so I should say, right away, right, so in characteristic 0, so Nakamae proved this. If X is smooth in characteristic 0. But actually, our proof is related to also, so we use ideas and techniques from Schoenkiel's paper on base point freeness in positive characteristic. Also, I guess we use. Okay, so again, so the theorem in characteristic 0 uses vanishing theorem. So that's the reason why one has to take a different approach in characteristic P. All right, so let me now state the second result. So now I want well, some sort of description, again, some numerical description of the non-nef locus. All right, so in order to do this, let me introduce some notation. So I want some function that measures whether some point lies in this non-nef locus or not. So whether some divisor should be positive, should be nef or not at a point. Right? And this is an asymptotic order of vanishing. So notation. So given L in a line bundle on X, I'll take AM to be the ideal defined defining the base locus of Lm. Okay, so what does this mean? So I give the definition of this base locus in right as a scheme. So if you translate this, what this means is that if I look at the evaluation map from H0 of Lm, tensor with OX, right? So this maps to L to the M. This is just evaluation of sections. And AM is a unique ideal such that the image of this thing is AM times L to the M. Okay? All right. So now the way you cook up a function, so again, so the idea is the following. So what you want to measure somehow the singularities of the base locus at various points. Right? So what I'll do, for every M, I'm going to look at the order at a certain point of this ideal AM. Right? So in other words, I'm looking at a general element in the linear system of L, and I compute the order of vanishing at that point. So if X is a point in X, and now let me assume that X is actually non-singular, right? So the order of vanishing at a point is well behaved. So then I'll define this asymptotic order of vanishing like this. So for L to be the infimum over all M at this odd X of AM over M. Okay, so again, what this means is that I take a general element in the linear system L to the M, and I look how much it vanishes at that point, right? And I normalize it, and I take the infimum. And this is actually also a limit. So that's not hard to see. Of course, well, it's a limit if I just restrict to those guys that are not infinite, right? So if AM is actually 0, then this would be infinite. So, but anyway, so if I restrict to those that are actually finite, in the case when some multiple of L actually has sections, then I get a limit. All right, so now let me state the second theorem. So Theorem 2. So this says that if X is smooth, and let's say L, a line bundle on X, is big. So big, what big means is that some multiple gives a map that has the same dimension, that's is generically finite over its image. And if I take a point X in X, then the following are equivalent. First of all, that X is not in this B minus of L. So in other words, L is, you should think L is nef at this point. So the second property says that this function vanishes at X. So this odd X of L is actually 0. And somehow the interesting thing is that you can actually also, so this is also equivalent with the fact that the set of all these numbers, odd X of AM, which are finite, let's say, over all M, this is actually bounded. Okay? So again, so what's the typical thing to keep in mind? So for example, what can happen is that if you look at various powers of L, for example, you might have a divisor that's always in this base locus. But on the other hand, it might show up in this base locus only with multiplicity 1. So again, this is typical, for example, when you have some ring of sections that's not finitely generated. And what this says is that in that case, this set is bounded. So then, of course, this is 0. But the point is that in this case, sorry, I messed up again. So the condition is that X is not in B minus if this happens, right? So, all right. So again, this was known in characteristic 0. One can say also something more generally when L is not big, but somehow the result is slightly more involved. It needs a couple more definitions. So again, in characteristic 0, this was proved by Nakayama and independently in a joint paper with Lawrence Hein, Rob Lazarsfeld, Michael Nakamaye, and Michna Popa. And actually, so what I'm doing here is just using somehow the approach in this paper, but somehow replacing a certain tool called multiplier ideals with something called test ideals that I will explain. Okay, but actually what I want to do, I mean, in the second half of the talk is actually to explain, to try to give you the feeling for somehow how you work in characteristic P using Frobenius in order to prove these sort of results. Right? So again, in characteristic 0, the proof involves vanishing theorems. Basically, you want to get some sort of global generation results, and you obtain them using vanishing theorems. So in characteristic P, you can use Frobenius for this purpose. So from now on, let me go and to say a few words about how to use Frobenius. All right, so remember, so the key object is this Frobenius morphism. Right, so this is the identity on the point, but it pulls back, it takes a function f to its pth power. So what properties does this have? So let me list a few things, right? So first of all, what happens if you pull back by the Frobenius line bundle? So if you think about the line bundle as a co-cycle, as a Czech co-cycle, right? Pulling back by the Frobenius raises the co-cycle to the pth power. So what you end up with is actually isomorphic to L to the p. Okay? So the second thing is what happens if I pull back an ideal, right? So if I pull back, let's say, yeah, so the ideal defining some subscheme. Right, so then what you get is the ideal that I write Iz to the p, which is generated. So this is the absolute Frobenius. Okay, so this is a Frobenius power of the ideal, so which is generated by fi to the p when the fi's are local generators. Fiz. Okay, so this is really just a definition. And the last property is what happens if I have a section. So let's say I have Z as here, and let's say I have a section of a line bundle L over Z. Right, so what happens when I pull back? Right, so if I pull back S, I get a section over this scheme that I write, okay, Z to the P, of L restricted to this scheme, of L to the P restricted to this subscheme. Right? So this is a section, but if I restrict it, if I go from this thickening of Z to Z itself, basically I just obtain the P power of S, so whose restriction to Z is actually S times P power. Okay? All right, so this thing is straightforward, but somehow let me illustrate this with a remark of Schoen-Kiel, which somehow shows you that in a surprising way, when you look at base loci in characteristic P, the reduced structure, I mean the non-reduced structure doesn't really matter. So so this says the following, that if Z inside X is closed subscheme, then if I look at B of L restricted to Z, so this stable base locus, this is the same thing as the stable base locus of L restricted to Z with a reduced structure. Okay, and the same, so again, this is, I think, appears in this paper of Schoen-Kiel that I mentioned, and the same for B+. Okay, so how should you think about it, right? So So if I have a section of L restricted to Z that doesn't vanish at a point, I can, of course, restrict it to the reduced structure, and it will still not vanish at that point. So the interesting part is that somehow you can go the other way. Right? So why is this true? Right? So I hope it's already clear because of this remark. Right? So if S is, for example, a section of L, let's say of L to the M restricted to Z reduced. Right? So what you do is you look at, so you have Z, let's say Z reduced. You have Z, which is an infinitesimal thickening of this one, but then you apply the Frobenius power as many times until the ideal of Z contains P to the E Frobenius power of the ideal of the reduced structure. Right? So in other words, until this one is contained in Z reduced to this P to the E. Okay? But then this remark says that if I have this section that, for example, let's say that S does not vanish, right? So F is, well, how should I write it? So let's say if Q does not lie in the zero locus of S, right? So then what you do is you pull back by the Frobenius over here, and you restrict to Z, and then again you get the section of Z over Z, not of L to the M, but of L to the M times P to the E, which does not vanish at Q. Right? So what you do, you use then F to the E, the pullback of S, restricted to Z. Okay? So again, this is something that, for example, this sort of assertion you don't have in characteristic 0, but it simplifies quite a bit the story, allowing you somehow to disregard the non-reduced structure. All right, so now let me say just a few words about the main ingredient in the proof of Theorem 1. So this is the main ingredient in proof of Theorem 1. So this is a proposition due to James, which says the following. So if L is nef, and if you have E to be an effective divisor, so an effective, of course, Cartier divisor, such that L, so again, basically what I'm doing, I'm writing L as an ample plus an effective part, right, such that L twisted by minus E is ample. Then what you have that the stable base locus of L is actually equal to the stable base locus of L restricted to E. And again, the same for B plus. Okay? All right, so now I hope, let me explain why somehow this is extremely relevant for Theorem 1. You see, the point is that, so what do you do when you want to look at this sort of augmented base locus? So for augmented base locus, basically you write multiples of L as some ample plus some effective part, and you just take the intersection of all the effective parts that you get in this way. But what this says is that if I look at some ample plus some effective, basically I can always restrict to this effective part. So somehow I can actually run an induction by dimension with a little bit of care. I mean, dealing with a non-reduced and non-irreducible structure. But basically, that's what you do. You do an induction on dimension. And here, it's actually very important that somehow you try to prove things not just for smooth varieties, but just for arbitrary projective schemes. So let me explain the proof since. So this is actually very related, with the results that Sean Keel has in his paper, but somehow it's at least the proof that I'll give simplifies a lot Sean's definition, Sean's argument. So again, this is due to James. So what you do is, of course, right? So again, there is one trivial inclusion, right? So if I have a section on a multiple of L, I can just restrict it here. So it's clear that actually, so let's see, so which part is clear? So So I guess maybe this one is clear. That's right. So basically what you want to start with the section of, let's say, of L to the M restricted to E, right? Such that, let's say, some point Q does not lie in the zero locus of S. Okay? All right, so now you look at the following exact sequence. So you have L to the M, just the usual one, L to the M restricted to E, and you have here L to the M minus E. Okay? So first of all, what's L to the M minus E, right? So I can think of this as L twisted by minus E, which is this ample guy. So this is L of minus E times L to the M minus 1. But now this guy is ample. This L is nef. So this is actually ample, right? So let me write this L prime, and this is actually ample. Okay? So now the advantage is that if I have something ample, right, if I take a large enough power, it has no cohomology. But I can achieve the large power just by pulling back by Frobenius. Right? So what this says is that H1 of X and the pullback of L prime is actually equal to 0 for E large enough. Right? Again, this is just some large power of L prime. Okay, maybe I don't want to do that. Let me move to the next. All right, so now, again, I hope it's clear, right, what you want to do, right? You pull back by Frobenius, right? So if I pull back by Frobenius, this part will have no cohomology, so I end up with something surjective. So what I have H naught of L, let me write it directly. The pullback by Frobenius will be M times P to the E, will surject onto L of M, the P to the E, restricted, I guess, to this thickening of E, which is P to the E times E. Okay, and here, over here, I have F, the pullback of S. Right? So what this says is that I can lift it to X, and of course, as we've seen, right? So this lifts to a section. And again, of course, by definition, essentially, right? Non-vanishing at this point Q. Okay, so this completes the proof, right? So again, the point is that you have this asymptotic vanishing for powers of ample guys, right? And somehow looking at this sort of stable base loci is very suitable in here, right? Because you allow always powers. So you cannot really lift things, but you can lift it for powers. Okay? So maybe that's as much as I'm going to say about the proof of theorem 1. So I want to say a little bit more about about the proof of theorem 2. So maybe I'll keep this on the blackboard, and I'll start doing some preparations. In characteristic 0, there is basically, so what's the yoga for proving this sort of things? You first prove some sort of global generation result for multiplier ideals, and you use that one in order to get these equivalent things. So somehow, I think that part is interesting, but somehow it's basically the same picture works in characteristic P. So what I'm going to do, I'm just going to tell you what is that technical ingredient and how to prove it in characteristic P. And maybe I won't say too much about how you actually get this sort of statement. So again, the technical ingredient for proof of theorem 2 is the following. Theorem 3. So again, so X is non-singular, projective in characteristic P, and I'm gonna take the following data. So H will be some fixed, very ample line bundle or divisor. So I'm going to have L and E in peak of X. And I'm going to take some parameter lambda. such that the difference I guess E. So again, now I'm going to write it additively. I hope there's no confusion. E minus lambda times L is actually nef. Okay, and then the statement is that the following sheaf, so I'm going to have to define this a little bit later. So this is lambda times L. Also again, so this is the asymptotic test ideal that I will define. So this is something that the way you should think about it is that, again, it's something that measures the singularities of the base loci of L. And this, if I twist this by the following line bundle of kx plus E plus dH, so this is globally generated for D greater or equal than the dimension of x plus 1. Okay? So again, don't worry too much about the technical details. So this one I still have to define. So what's here to note, right? So basically the condition is that I have this fixed, so you should think of this dH as some sort of fixed, very positive guy that appears. And then I know that the difference between E and whatever symbol I have here, lambda times L, so this is weakly positive in the sense that it's nef. And then I get this global generation of this sheaf. Okay, so maybe even before I define what this is, let me still say one word to show you why this sort of global generation, this sort of uniform global generation is relevant. All right, so again, why relevant? So suppose that, right, so suppose X is a point that does not lie in the vanishing locus of this test ideal, whatever that means, of M times L. Right, so I have these closed subsets cut out by these ideals, and I assume that this does not lie in this locus for every M. Okay, so in particular, this says that, right, so this ideal does not vanish at this point, but this guy is globally generated. So what this means is that I'm going to get sections of this one. So I'm going to apply it, right? I'm going to take E to be actually equal to maybe M times L, and lambda to be equal to M. Okay, so of course, the difference is nef because it's actually just 0. So what I get that X does not lie in the base locus of what? So what do I get here? I have L to the M. Again, I'm writing it additively, so it's ML plus some fixed part that's Kx plus this D times H. But D is fixed, right? So basically what I'm saying is that X does not lie in this base locus. So in particular, I can just erase the base locus here. I can erase the M. And then what I have here is L plus some small multiple of this guy. Okay, so basically, this implies, I mean, this might not be ample, but I can add a little bit to make it ample. And then what I concluded that actually X does not lie inside B minus of L. Okay, and the converse also holds. So this is actually part of the proof of the theorem. Okay, so, but it's a bit of a long story, so I don't want to say much more. I just wanted to show why this sort of uniform global generation statement is helpful when you look at this base loci. All right, so now, before I give the definition, let me say a couple of words about history, or I guess it's recent history. So again, so this relies on ideas. Right, so Theorem 3 uses ideas of Keeler, who used them somehow to give a new look at in the simplified proof of Fujita type results in characteristic P. And I understand that Hara also has this, but unpublished. But somehow most relevant from this point of view is some recent work of Carl Schmid, who I think is the first one who noticed that these results of Keeler can be put in the form of global generation results for involving the test idea. So in particular, he has results that are similar to this one in the non-asymptotic setting. Okay, all right. So this is about the statement. So now let me try to give you, I'll try to actually prove this theorem, so if I have time. So let me say a few words about how do you measure singularities via these ideals. All right, so definition of test ideals. All right, so again, these are objects that are due to Hara and Yoshida. So basically, they come from tight closure theory. But I'll use a more geometric definition, which was John Blickle and Karen Smith. All right, so what I want to do is the following. So I want to look at a map, a surjective map that you have like this. All right, so there are various ways of thinking about this map. So you can think of it as some sort of trace map for the Frobenius, which is in our setting, it's flat and finite. Or you can think of this as coming from the Cartier Isomorphism. The Cartier Isomorphism says that the cohomology of the push forward by the Frobenius of the de Rham complex is, again, given by the differential form. So the last term goes from this push forward of the de Rham complex basically to omega x. Omega x is the cohomology. So this is, but this is actually something extremely concrete. So basically what you do is, if you have x1 up to xn local coordinates, so how is the map defined? It goes from x, so let's say I have the product of x alpha to the I alpha dx. It goes to the product of x alpha to I alpha minus p minus 1 over p times dx. Okay, so of course, what I mean is that this is 0 unless all the exponents are integers. Okay, so I mean, one way to think about it is that basically what you are doing is extracting some sort of p root, right? But in some sort of smart way. So all right, so how do you get out of this picture these test ideals? Right, so now given an ideal B inside OX, I want to take some sort of inverse Frobenius power. So the way I'm going to do it is that I'm going to apply the iterate of this map. So let's say this map is TR from trace. Right, so I'm going to look at f to the e lower star of B times omega x. Right, and the image will be some submodule of omega x. Again, omega x is a line bundle, right? So the image will be something that I'll denote by B1 over P to the E times omega x. Okay, so this defines some sort of inverse Frobenius power for ideals. All right, so now if lambda is a positive, let's say, I guess not necessarily rational, real, so what you see is that if I look at a to the roundup of lambda times p to the e, and then if I take this inverse Frobenius power, 1 over p to the e, this is a non-decreasing sequence of ideals. So this is non-decreasing. So by Noetherianity, it stabilizes. So it stabilizes at this test ideal, at tau of a to the lambda. Right? So I mean, so one way to think about it is that what you are doing is somehow you mix powers of the ideal with this sort of interesting operation, which is taking inverse Frobenius powers. And then you get the test ideal. So of course, I mean, the philosophy is that these test ideals give analogs in characteristic P of multiplier ideals. And in particular, they satisfy many of the formal properties of multiplier ideals. Without, of course, the main exception is the fact that they don't satisfy vanishing theorems. Right, so how do you prove, for example, this sort of statement in characteristic 0? So basically, you want to prove that something is globally generated. So you use Castelnuovo-Mumford regularity plus vanishing theorems. Right, so the vanishing theorems basically tell you that the multiplier ideal twisted by something which is positive has no cohomology. And then by Castelnuovo-Mumford regularity, you get this statement. Okay, so now the point is that I'm going to use, again, Castelnuovo-Mumford regularity, but you don't have vanishing of cohomology in this setting. Also, but it turns out that Frobenius allows you to get rid of this vanishing. All right, so again, so what I have here is some sort of construction, this test ideal construction that gives you some ideals associated with other ideals and which measure somehow the singularities of something. So what I want now is that given L, a line bundle, so I want some sort of asymptotic construction that measures the singularities of all the AMs. Right? So again, let me remind you that AM defines this base locus of L to the M. Right? So in particular, it's an immediate remark that if I take AM to the R, this is contained inside AM R. So in other words, it's what's called a graded sequence of ideals. So exactly as in the case of multiplier ideals, you use this remark to show that AM to the lambda over M is actually contained in the test ideal of A MR to the power lambda over MR. Okay, why is that? It's because this one contains the corresponding test ideal for AM, let's see, to the power R times lambda over MR, right? Because of this inclusion, and this is precisely this statement. Right, so the interesting part here is that then, again, by Noetherianity, this thing stabilizes if M is divisible enough. So you get some sort of asymptotic measure of the singularities of the base loci. All right, so now this test ideal of lambda times L is by definition the test ideal of AM to lambda over M, where M is divisible enough. All right, so now let me prove actually this theorem. All right, so we have first of all to deal with this gadget, with this sort of asymptotic test ideal, right? So what you do is, first of all, you fix some M such that this test ideal tau of lambda times L is actually the test ideal of AM to the lambda over M. Right, so M will be fixed, but then I'm going to use the definition of the test ideals to actually express this. Right, so this will be equal with this inverse Frobenius power, so it's AM to the round up of lambda over M times P to the E, inverse Frobenius power 1 over P to the E. Okay? All right, so now I'm going to use the definition over here. All right, so what does this definition say is that if I have f to the e lower star, so what ideal do I have here? So it's AM to this round up of lambda over M times P to the E times omega x. So this subjects onto this asymptotic test ideal of lambda times L. Okay? All right, but of course, then I tensor with whatever I have left here. So I tensor with the corresponding line bundle. Right? So again, so on the right-hand side, I'm going to get the sheaf we want. So what I'm going to get on the left, so again, I get something surjection. So I get f to the e lower star. And then I get, of course, this ideal, lambda over M P to the E. And then I get, so I'm going to use the projection formula, right? So this would be omega x twisted by, so let's see, what do I have here? So this is omega x, and then I have to add this p to the e times e plus dh. All right, so this is what I have here. But now a to the m appeared as the image of something, right? So again, the left-hand side is the surjective image of the following gadget, right? So remember that AM was the image of copies of O of minus ML, right? So if I have a power, basically, I have to take this into account. So what I get, let me write it here. It's omega x with p to the e plus dh. All right, and then what I have again minus m times the roundup of lambda over m times p to the e times d times l. Okay, so the upshot is that what I need to show that this one is globally generated. Right? So this is globally generated. All right, but let's say, let me write this as curly f. Okay, so basically we are done. Because, again, by Castelnuovo-Mumford regularity, it's enough to show that hi of x and f twisted by minus ih is 0 for I between 1 and the dimension of x. Okay, so this means that actually it's 0 regular in the sense of Castelnuovo-Mumford, which implies that it's globally generated. But then what's this expression? Right? So this is equal to hi of x. So again, I can ignore the Frobenius direct image, right, the push forward, because I just care about the vanishing. So by the anyway, so this is a finite map, so I don't care about it. So what am I left with here is omega x twisted by p to the e times e minus m round up of lambda p to the e over m plus p to the e minus I times h. Sorry, p times p to the e times, sorry. So it's p to the e times d minus I times h. All right, so I'm already over time. So let me finish quickly. So what's the point here? So now for simplicity, let me just assume that lambda is an integer. Lambda is, for example, let's say that you don't have this roundup, right? So if you don't have the roundup, m simplifies with m. So what you get here is p to the e times e minus lambda d, which is a nef divisor. And then what you have here, because d minus I is at least 1, so then you have a large multiple of an ample line bundle, right? So then by some asymptotic version of, by some version of the asymptotic Serre vanishing for large multiples due to Fujita, you get the vanishing if E is large enough. So in general, since lambda is a rational number, you can actually tweak this a little bit to make it some fixed sheaf times an F divisor. So anyway, so this is equal to 0 by something called Fujita's theorem, Fujita's vanishing theorem, which is, again, maybe I should say what this theorem says. So it's an asymptotic, right, so Serre asymptotic vanishing says that if I twist a sheaf by a large power of an ample line bundle, this is 0. So what Fujita says is that I can do this in such a way that I can also twist by an arbitrary nef line bundle if the multiple of the ample guy is actually large enough. So this is exactly what comes in the picture. So I'm sorry I went over time. So thank you.
question.